You can see the screen, right, Ibrahim? This arc.
Yes, sir.
Yes.
Achha, so we did we were doing isomers basically. So in isomers we did cisplatin, we did transplatin, we did cis and trans isomers uh, while we were doing these ones. That the ligands can sort of be arranged in different ways. Uh, the ligands could be on opposite ends, and the ligands could be right next to each other. So there's a cis version, there's a trans version in octahedral complexes, and there's one in square planar complexes. This was probably the only square planar complex that you had to study, which is cis and transplatin. Now, what we're going to do is we're going to do stereoisomers. I think that's the very last thing. Okay, but then we'll start doing past paper questions. So stereo isomerism, like optical isomers. Stereoisomer, not stereoisomer, because stereoisomer includes geometric. I'm talking about optical isomers. The specific version. So optical isomers were that they had exactly the same, they were mirrored versions basically. They were mirrored, non-superimposable. Imposable complexes, arrangements. Right? So for example, I said now there's only one which you basically have to cater for, and let me be specific. Let me just open the syllabus. The only one that you need to talk about. So stereoisomerism and transition metal complexes. So the optical one is the one with nickel. It's a bidentate ligand. So you have a nickel line, and it's got a dative bond on top, a dative bond on the right side. So that's your z-axis. There's one on the, let's say that's your x-axis. Then there's the y-axis. Okay, so this, and it's with ethane 1,2-diamine, which is going to be your NH2, and there's going to be another NH2, and there are going to be two CH2s. Okay, so you got a carbon chain. So that is one bidentate ligand attached to the nickel line. And then I have another bidentate ligand which is going to be attached. So that's going to be, to look quickly, NH2, NH2. And I've got two CH2s. And then there's a third one. You can remember optical isomers. Remember chiral centers in AS. That's a NH2, NH2. And then there are two CH2s. Okay, and then there are lone pairs. So now I have to draw a mirrored version. Also, I would get rid of this just to show you that this is going into the page. So I'm drawing a dotted line. So that shows that that's your X, Y, and Z axis. Now there's going to be a mirrored version. Hopefully I can just flip it as it is. 1 second. Is there an option to flip this? No. Okay, So you can, so you'll be asked to draw this. So what I'll do is I'll try and be quick. Now you have to draw the exact mirrored version. Okay? This is what you're familiar with doing this in AS Organic. So you have to draw the exact mirrored version. So everything has to be flipped around, left to right, either inverted left to right or top to bottom. So if I try to invert this, it's going to look like this. The NH2 would be on the other side. TK got CH2s. So then the top one, it's going to shift to the left. So I've got NH2. I've got NH2, and I've got two CH2s. And this one also shifts to the left side, so it's going to be NH2 and NH2, and then there could be two CH2s in the middle. So these are two mirrored versions. And just like your two hands, left and right hands, this particular arrangement has no line of symmetry or plane of symmetry. So no matter what you do, they're non-superimposable. No matter how you rotate your right hand, it never looks like your left hand. Although they look kind of exactly the same, but no matter how you rotate the right one, it's never going to look. So there's going to be a right-handed version, and there's going to be a left-handed version. Okay, is this clear? The two types, the optical isomer in transition metal complexes. Is this clear? Hala, is this clear, Qasim? Isaac?
Yes. Yes, sir.
Yes,
Okay.
sir.
So, but you just have to remember this. And plus, I guess that's it. That's all about transition metals. And let me just open the syllabus once more. I've sent you the notes. I said based on this, we'll talk about K-stab now. We did talk about K-stab 1 second. We've already done with K-stab. Well, we can discuss that later. There's only one final thing is just one very, very last thing, and that's polarity of complexes. Okay, I'm going to post all the videos as well, polarity of complexes. Now this is pretty straightforward as well, that based on what the complex looks like, you can figure out the polarity of the complex. For example, if I have a complex where I have copper, and it's got three Cl ligands attached to it. So there are three Cl ligands attached to it. And on one side you have, let's say you have a neutral water molecule. Now you'll be asked basic questions whether this ligand this complex is going to be polar or not, which I suspect it's going to be polar because Cl is more electronegative. So the electrons are going to be closer to Cl, right? So one of the sides would have slightly more negative charge compared to the water, which is already neutral. So that side is neutral. So it might be positively charged. So it's just simple. You already know about polarity in molecules. So the same concept is going to be applied. If someone is more electronegative, electrons will shift to that side. TK, is this clear? Clear? Can you clear? Qasim, clear? Isaac, Ibrahim, Hala, is this clear?
Yes, sir.
Chalo, theek hai. Now what we'll do is we'll just start with past paper questions. And we just have a look at the notes. There's not going to be anything I mean, there's going to be very little stuff that you would have to think about. Whatever's in the notes, you just have to copy paste that. So for example, he's talking about copper 2 salts. He's talking about copper complexes. He's talking about what's going to happen when it reacts with NaOH, and it's talking about what's going to happen when he reacts it with concentrated hydrochloric acid. Yeah, that's the. So we did this in detail. So we just go back and have a look at the ligand exchange reactions that are going to happen. TK, where's copper? 1 second. So we did all these ligand exchange reactions. We did the drawings as well. TK for copper and for cobalt. So this is on your screen, right? It's you have copper surrounded by water molecules, right? So that is copper ions floating in water, right? So they are datively bonded to water. So it's copper, and this one is CuH2O6. You add NOH to it, then the OH ion or the OH ligands, they attack and they replace the water. So copper gets surrounded by OH ions and the water gets knocked out. But the thing is that when they get surrounded by OH ions, it becomes neutral and the water no longer sticks to it because copper plus 2 and OH ions together, this part would be neutral, this entire part. Okay, that's going to be neutral. And the water molecules are no longer going to be attached to it. So you'll get a COH2 solid precipitate. When you add ammonia to it, the water molecules get knocked out and ammonia replaces the water, and it could be any number of water molecules getting knocked out. It could be 4 NH3s, it could be 6 NH3s and 0 water molecules. And then when you add concentrated HCl, the water ligands, they get replaced by Cl ligands, they're lone pairs. The copper ions, they start attracting Cl. Cl is bigger in size, so you don't get an octahedral complex. What you get is a tetrahedral complex, right? So you go back, you have to write the ionic equation. So I have Cu H2O6. I am adding OH ions to it. Okay, this is +2. So I'm adding OH ions to it. What's going to happen? It's Cu +2 and OH ions are going to get together. And they're going to form a precipitate. They're going to lose the ligands because this is going to be neutral. So the water molecules and the lone pairs are no longer going to be attracted to the CuOH2. And this particular reaction is known as precipitation or ionic precipitation because a solid pale blue precipitate is going to be formed. Right? So color and state of the copper containing, so it's a pale blue precipitate, it's a solid, right? That's the answer to this part. All of this is going to be written in the notes. It's you're getting this in do you remember I told you it's not, I mean, the orange over here, this reaction over here is not ligand exchange, it's precipitation. And I gave you the equations for all these reactions as well. Do you have the equations for all of these ligand exchange reactions? And most of the time, they're going to just ask you this. So next one is, so there's just 4 or 5 reactions which you just have to memorize. Concentrated HCl, what's going to happen? The ionic equation. So you have CuH2O6. And again, it's +2. The Cl ligands are going to attack. And 4 of them are going to get attached because, and it's going to be -2. So copper is +2, Cl is -1. And the 6 water molecules get knocked out. Now this is proper ligand exchange. One ligand got replaced by another ligand. This color was, I mean, it was greenish yellow. And the state was, it was an aqueous solution. So you can just write solution. I mean, this thing is, floating in the solution, so aqueous solution. Okay. Is this clear?
Yes.
Okay, this one is a moles question, by the way, but let's do this. Actually, it's got nothing to do with transition metals. We'll do that later on. It's a moles question. Okay, he's asking for the next question is he's asking for the what is he asking for? He's asking for the electronic configuration of copper plus 2, right? Copper has 29 electrons. Its electronic configuration is 2p6, CS2, 3p6. 4s is filled first, and then there would be 9 electrons in the D, right? That's how the electrons are filled. But copper is a special case in a way that instead of 3d9, it's actually 3d10, and 4s is actually 1, right? So he's talking about the copper 2 ion. So that means the outer electrons are gone, the 4s is gone, and there's going to be 1 electron gone from the 3d as well, so you'll be left with 3d9. And again, the next question is exactly the same. Remember, I told you they're going to repeatedly ask you the same question over and over again. Over here, they're just asking for the colors. So that's your blue solution, and that's your greenish yellow solution. And then you get this larger question where you have to write the whole explanation of why do different ligands have different colors. Remember, I told you that there would be 2 questions. One would be that why are they colored, and the other one would be that why do different ligands are going to have different colors, right? So I'll just recap the color thing, right? So why were transition metals colored? Well, if your screen lag to nahi kar rahi is the middle is the screen lagging?
No.
ठीक है. Acha, so if you have these this is your d-subshell, right? You've got dxy, dxz, dyz, dx square minus y square, and the 5th one is dz square. Now, the dxz and the dxy, the electron density lies between the axes, right? It's not on the axis. It's between the x and y axis. It's between the x and z axis. In the dyz, it's between the y and z axis, right? So the electron density in the first 3 is between the axes. In the last 2, the dx2 minus y2 and the dz square, these 2, the electron density is right on the axis, on the x and y axis, and over here it's on the z axis. So 3 orbitals have electron density between the axes, 2 of them have electron density on the axis. So first thing, your 5 of the d orbitals, they're all degenerate, which means that they have exactly the same energy level. 3 of them, the electron density lies between the axes, 2 of them, the electron density lies on the axis. Now, when a complex is formed, you have the ion in the middle. Okay, so this is how the complex is formed. You have the ion in the middle, and you have this incomplete d-subshell, which is not bonding actually, but it's there. And the water molecules, they're lone pairs, they come and they stick to the copper plus 2 ion, right? So they surround it. Now, if the ligands are approaching on the axis, and they have their lone pairs approaching on the axis, so within the atom, inside the atom, it kind of becomes harder to keep the d electrons on the axis. Why? Because all your ligands, they're approaching or they're sticking on the axis, right? So all of them, they're on the axis, so it's harder to keep electrons on the axis. In the dz square, in the dx2 minus y2, But it's kind of easier to keep electrons between the axes, right? Because the ligands are further away from there. So what happens is that your d-subshell, which was originally it was degenerate, it splits. And when it splits into two energy levels. One area on the axis, it's harder to keep electrons. Between the axes, it's going to be easier to keep electrons. So the energy level, there's going to be an energy level gap. So why are they colored? They're colored because this energy level actually matches frequencies that belong to the visible spectrum. The electrons from the lower energy d-subshell will jump and can go into excited state and can occupy the, so remember the d-subshell has to be incomplete. Otherwise, the electrons cannot jump to the higher energy d-subshell. That is one of the definitions of a transition metal complex, that that a transition metal is supposed to have stable ions with incomplete d-subshells. So electrons would jump and go to the higher energy, but for that they would need to absorb frequencies. And those frequencies, luckily, they belong to the visible spectrum, which is why you see complementary colors. So if the transition metal is its electrons are going to absorb the blue frequency, you're not going to see the blue frequency. The blue frequency is not going to be reflected back. So you're going to see the other colors, but you're not going to see the blue color. So that was the entire story. And why do different ligands have different colors? The reason for that is that different ligands will have a different repulsion. I mean, their lone pairs are different and they will exert a different repulsion. So this energy gap that is going to be created is going to be different. And if that energy gap is different, a different frequency is going to be absorbed. Okay, so we wrote down these two answers, which is, so I'm not going to copy the answers because it's written in the notes. The first one is why are transition metal complexes colored? So if you can see on the screen, it's due to repulsion from lone pairs on ligands. The d-subshell splits into two energy levels. Electrons from the lower energy d orbitals can absorb energy and jump to the higher energy d orbital. And since energy is proportional to frequency, or since E is equal to HF, the energy gap delta E between the d orbitals exactly matches frequencies that belong to the visible spectrum. And hence you see a complementary color, right? But that is the answer for if they're going to ask you, why are they colored? If they are asking you, okay, why does ligand exchange changes the color? Why do different ligands have different colors? In that one, you're going to write that different ligand and lone pairs have different charge density. Hence, they're going to exert a different repulsion. And the energy gap delta E created between the d orbitals is also different. And since E is equal to HF, a different frequency from the visible spectrum is absorbed, hence a different complementary color is seen. Okay, so that's your, although it's just going to be 2 marks, one would be about, they'll give you 1 mark for that different ligands and the different lone pairs will exert a different amount of repulsion. So and therefore a different amount of energy gap is created. So you clear up both of these things, both of these answers. Is that clear? Qasim clear, Isaac, Ibrahim, Minal. Is this clear?
Yes.
So, and similarly, there's going to be a third question, which is written in the notes as well. Why are copper 1 and silver 1 salts colorless? So I'm going to go back to the notes. Now, for them to be colored, it was important that the electrons can go into excited state, right? The electrons can jump and they can move to the high energy d-subshell. Now, the issue is for that to happen, I mean, there must be room available, right? I mean, if they're full, the electrons can't jump around, right? They can't go into excited state. So there's got to be room available so that electrons can move to the high energy d-subshell. So what happens in the copper 1 salts is, so the question is, why are copper 1 salts colorless? So the reason they are colorless is that the D is completely full in copper +1. Okay, it's completely full. It's completely full. So you're going to write that the d-subshell is full and the electrons cannot absorb frequency from visible spectrum and move from low energy d-subshell to the high energy d-subshell because there's no room available. So they can't jump to the higher energy d-subshell. Okay, Isaac, is this clear? Brain clear?
Yes, sir.
So I just wanted to show you that everything that's in your notes, they're going to ask you. There's hardly going to be any tricky questions. I said this one is about K-stab. We can do this. So it's about K-stab. What was K-stab? K-stab was that when you have a ligand exchange reaction. I'm going to revise what K-stab was. Where did we study? I think it was before this. Yeah. So K-stab was that it was the equilibrium constant for a ligand exchange reaction. So you have especially when a complex is in equilibrium with its aqueous solution. So copper with water, you add Cl ions and copper is now with Cl, right? So you have a ligand exchange happening. Product concentration divided by reactant concentration, that's K-stab. K-stab is the equilibrium constant for a ligand exchange reaction. You don't write water in the expression because water is in large excess. And so that's not written in the expression. That's it. So if K-stab has a larger value, if it's greater than 1, that means ligand exchange will happen. You'll get products. There's going to be more products formed. And that would also indicate that the product complex is more stable as well because it's getting formed. So going back to this, so this is your K-stab given for a ligand exchange reaction. So it's silver with water. Okay, so you have silver with water. It's going to be a complex. And ammonia comes in, and now silver is with ammonia, and it's forming a complex. But anyways, the first one is about the solubility of AgBr, and you have to calculate the solubility of AgBr. And they've given us KSP. So this is from the last chapter. Okay, what was KSP? So KSP was when a salt dissolved, right? It was the equilibrium constant of a salt dissolving in a saturated solution. So it's going to be product concentration, Ag +1 and Br -1. And divided by the reactant concentration, which is AgBr solid. You don't write solids in the expression, okay? So that's what KSP is. Now he's asking for the solubility. So we're going to assume that in a saturated solution, X mole per dm cube dissolves. So in a saturated solution, the amount of ions would be X, and Br ions would also be X. So my KSP would be 5 times 10 power minus 13, which is given. The concentration of silver ions is X, and the concentration of Br ions is also X. So what do we get? Well, what is X then? X would be and it's going to get under rooted. You tell me what the value is for this. Minel, kya aa raha hai? What's the value? Isaac, Ibrahim?
7.07 times 10 power minus 7.
So that means there's very less solubility. The amount of ions that are being produced in the saturated solution, that's very, very less, which means AgBr is not soluble, right? Now, in the other part, he's asking, use Lee-Shatler principle as applied to equilibrium 1 and 2 to suggest why AgBr dissolves in concentrated NH3, right? Well, the thing is, if you look at the second reaction, the K-stab value is like really large. I mean, the K-stab is like really large. It's 1.7 times 10 + 7. So that means this equilibrium number 2 is completely shifted to the right. So you're going to write that the K-stab is large. And therefore, it is, you can write that it's shifted to the left. Which means that the Ag+1 aqueous concentration is going to be very low. I mean, this Ag+1 concentration is going to be really low because all of it is going to react with ammonia and it will turn into the complex, right? So the Ag+1 concentration is low as it turns into the AgNH3 twice complex, right? I mean, is the first part clear? You clear? Isaac, Ibrahim, Middle, is this clear, Qasim? Hala, is this clear?
Yes, sir.
So the question is, why does AgBr dissolve? Well, when you add ammonia to it, ammonia reacts with Ag+1 and converts most of it to AgNH3 twice, right? So the Ag+1 concentration decreases. Now we're going to use the Lee-Shatler principle. So how would that affect the first reaction? If the Ag+1 concentration decreases, right, in the first one, where would that equilibrium shift? That's going to shift to the right. Okay, but the Lee-Shatler principle is that if the concentration decreases, it's going to shift to the right. So as Ag+1 aqueous concentration decreases, because most of it combines with ammonia, the equilibrium number 1 will shift to the right to produce more Ag+1. Is this clear?
Yes.
Yes. Ibrahim clear, Saak, Hala, Qasim, is this clear?
Yes, sir.
अच्छा फिर use equilibrium 1 and 2 to construct the equation for the reaction of AgBr with concentrated NH3, right? So I mean this one, the top one, right? So they're asking you to construct so I'm going to do it at the top over here. You just add the two reactions up. That's it. The overall equation. He's asking for the overall equation. AgBr is solid. That's the first one. It's going to be Ag+1 aqueous plus Br-1. And then it's the second one, it's Ag+1 aqueous plus 2 NH3 aqueous, and it's going to form AgNH3 twice. Okay, so you just add the two reactions up. AgBr with concentrated ammonia. Things that appear on both sides, that's going to get cancelled out. So what you're left with is, it's going to be AgBr solid plus 2 NH3, that's aqueous. And in the product side, it's going to be AgNH3 twice plus and Br minus 1. TK, is this clear? That's the overall reaction.
Yes, sir.
And then he's saying write an expression for the equilibrium constant of equilibrium 3 in terms of KSP. So now this one is tricky. So he's saying in terms of KSP and K stab, right? So remember, so look at the 3 reactions. Okay, the third reaction is actually the combination of the bottom 2 reactions. So I think ये apart next time करते हैं, उसमें time लग जाना है. This we'll do tomorrow, ठीक है? Okay, how is the equilibrium of this? How can you express it as a combination of KSP and K stab? ठीक है, we'll do that. We'll do that tomorrow then. ठीक है?
Okay, sir. Allah Hafiz.
चल. Okay, Allah Hafiz.